Hello everybody. This is a question, a problem about application on Archimedes principle. And it's actually not an easy one to do. So let's do it together. It says here there's a box, as you can see, and this box is floating in water such that 1/3 of its dimension, or 1/3 of one of its dimensions is underwater. So if this dimension is x, so here I'm going to say 1/3 of this side is submerged underwater. And they also tell you that ignore the thickness of the box itself so that you don't have to worry about the volume of the box or the dimension of the box as a material itself. All right? So this box, as it's floating down here like this, you start pouring water into it, okay? And as you are pouring water, more and more water into it, it starts sinking because of the water weight. And at some point, all the box is submerged and water from the surroundings start going into it. The question is, they want you to find how high the water in the box edge when the whole box is submerged underwater. Okay, just when it starts to be submerged underwater. Okay, now how do we do this problem? Now, when this is submerged, because there is water here in this area all the way, okay, it is submerged because of two forces acting down. The force, the weight of the force coming from the weight of the box itself. So I'm going to say weight of the box, okay? And there is another force, which is the water, okay? The weight of the water inside, okay? And what's pushing on the box up is basically the buoyant force coming from Archimedes' principle. We know that the buoyant force, FB, must be equal to now W, weight of the box, plus weight of the water. Buoyant force here is actually equal to the weight of the displaced fluid. Weight, and the weight of the displaced fluid, which is the water, because when the box is submerged, the water is being displaced, so it's equal to mass of the water times gravity, but mass of the water is equal to the density of the water times the volume of the water that has been displaced times gravity. Okay, now rho comes down, the volume of the water has been displaced. If this was x, like the side of the cube, then the volume of the cube is x times x times x, which is x cubed. And G comes down as it is, okay? So that's actually the buoyant force, all the buoyant force acting on the box. Now, this has to be balanced by the weight of the box itself, which we still don't know, plus the weight of the water, okay? Now, I'm gonna write this, the weight of the box. We still don't know what that is. So we have here WB plus the weight of the water inside the box when it's submerged. And we know it's up to H inside the box. The water level is up to H, okay? So now, let's find out what that weight of the water is. The weight, basically, in general, the weight of the water is equal to mass times gravity. That's mass of the water, okay? And mass is equal to the density times the volume times gravity, okay? Now, what is the weight of the water? The weight of the water, rho, comes down. The volume is x, this side, and here, x, and here, h. So it's going to be x times x, which is x squared times h. That's the volume of the water inside the box when it starts to be totally submerged, and times G. Now, everything here is moderately known. We still need to know what the weight of the box is. And that comes from the initial situation that we started with, which is what? 1/3 of the box is submerged totally underwater when there is nothing in it. Okay, so the weight of the box, WB, since it's at equilibrium with the other force, which is the buoyant force, we just need to find what the buoyant force here is, which is going to be equal to WB. Okay, the buoyant force is known as the weight of the displaced fluid. Now, how much weight of the displaced fluid is? It's weight of the water that was displaced, which is mass of the water that was displaced when it's 1/3 submerged, times G. Now, mass of the water is equal to rho times the volume of the water when it's totally 1/3 of it is submerged, times G. Okay, and that equal to rho, this will be here x times 1/3 of x, so x cubed divided by 3 times G. Okay, now this, the weight of the water, is equal to actually the buoyant force for this one, and buoyant force is equal to the weight of the box. So take this and put it here. So this whole thing comes down as it is. Rho x cubed G is equal to, take this one here, rho x cubed divided by 3 times G, plus this comes down, rho x cubed x squared h G. Now G with G cancels because it's in every term of the equation. What else cancels? Rho, the density, cancels, so it doesn't matter, right? Now we are left off with this equation. X cubed is equal to x cubed plus 3 plus x squared times h. And the only unknown in this equation is h, because they tell you in the problem what the dimension of the box is. So whatever the dimension is, here we have it as, for example, 7.08. It doesn't matter. Some problems will have different dimensions. Okay, but once you plug that in, this is the equation. The only unknown in this equation is h. For my problem here, x was equal to 7.08 meters. All right, so if I want to plug that in here, before that, maybe it's a good idea just to do a quick estimation. So this is x cubed minus x cubed over 3 is 2 over 3 x cubed, and that must be equal to x squared times h, divide by x squared, so this goes away with the cube. All right, so basically we have 2 over 3 x, which is 7.08, must be equal to h, and that should be the answer. This is just using your calculator, then you can find what the h in meters. Okay, and that's it for the problem. I hope you enjoyed it. It was really a good one. Thank you.